Electrochemistry, Part 4, Cell Potential under Non-Standard Conditions. For this video, we will be explaining the relationship between deviations from standard cell conditions and changes in the cell potentials. That's right, folks, we're going to get rid of that little degrees symbols off of our E's. The little degrees symbol is how we quickly denote that a process is occurring under standard conditions, 25 degrees Celsius, with all the reactants and products in their standard states. That is, 1 molar solutions, 1 atmosphere gases, and pure solids. This makes Q, the reaction quotient, for any reaction at standard conditions equal to 1. As an electrochemical reaction under standard conditions proceeds towards equilibrium, the magnitude of E, the cell potential, decreases, closer and closer to 0. At equilibrium, the cell potential is 0. That's also when Q is equal to K and delta G is equal to 0. In a real system under non-standard conditions, the cell potential will vary depending on the concentrations of the reacting species. The cell potential is a driving force toward equilibrium. Recall that cell potential is also known as electromotive force. You can somewhat easily predict how the cell potential under non-standard conditions compares to the cell potential under standard conditions by considering whether it is further or closer to equilibrium. If the non-standard cell is farther from equilibrium, so if the non-standard Q is farther away from K than a Q of 1 is from K, then the magnitude of E increases. It gets more positive or more negative, therefore farther away from 0. If the non-standard cell is closer to equilibrium, so if the non-standard Q is closer to K than a Q of 1 is from K, then the magnitude of E decreases. It gets less positive or less negative, therefore closer to 0. Of course, if the non-standard cell is at equilibrium, so if the non-standard Q is equal to K, then E is 0. Let's take a moment to look at each type of electrochemical cell individually. Recall that for a galvanic cell, the process is spontaneous in the forward direction, so that means that K is greater than 1. It's product favored. Deviations from standard conditions that take the cell farther from equilibrium, decreasing Q, bringing it further from K, will increase the magnitude of the cell potential, so it will be more positive, more thermodynamically favored than a standard cell potential. Deviations from standard conditions that take the cell closer to equilibrium, increasing Q, bringing it closer to K, will decrease the magnitude of the cell potential, so it will be a less positive, less thermodynamically favored than the standard cell potential. At equilibrium, the cell does not have a cell potential. E is equal to 0, because there's no longer any driving force for the reaction to take place in either direction. Q is equal to K, and neither the forward nor the reverse reaction are thermodynamically favored. It's at equilibrium. Recall that for an electrolytic cell, the process is non-spontaneous in the forward direction, so that means that K is less than 1. It's reactant favored. Deviations from standard conditions that take the cell farther from equilibrium, increasing Q, bringing it further from K, will increase the magnitude of the cell potential, so it will be more negative, more not thermodynamically favored than the standard cell potential. Deviations from standard conditions that take the cell closer to equilibrium, decreasing Q, bringing it closer to K, will decrease the magnitude of the cell potential, so it will be less negative, less thermodynamically favored than the standard cell potential. At equilibrium, the cell does not have a cell potential. E is equal to 0, because there is no longer any driving force for the reaction to take place in either direction. Q is equal to K, and neither the forward nor the reverse reaction are thermodynamically favored. It's at equilibrium. Are you confused yet? If so, then stop the video and play it over again from the beginning before moving on. Or just remember this, the focus is on the magnitude of E. If the reaction is farther from equilibrium than it would be under standard conditions, E has a greater magnitude. It's further from 0. If the reaction is closer to equilibrium than it would be under standard conditions, E has a smaller magnitude. It's closer to 0. It may be tempting to think about this using Le Chatelier's principle and justify your prediction of E compared to E naught with Le Chatelier's principle, but don't. Le Chatelier's principle only applies to a system that's already at equilibrium. If an electrochemical cell is already at equilibrium, it's a dead cell. E is 0. If E is not 0, then it's not at equilibrium, or at least, not yet. Here is a handy summary of the spontaneity of electrochemical cells. Pause for a moment and take it in before moving on. Here we have an electrochemical cell and its standard cell potential of positive 1.36 volts. That means it's a galvanic cell with a potential of positive 1.36 volts when the concentrations of all species are 1 molar. What happens to the cell potential if the concentration of cerium-4 were increased? Does the cell potential increase or does it decrease? If the concentration of cerium-4 were higher than 1 molar, then it would give us more reactants in this product-favored reaction, and that would make this spontaneous reaction farther from equilibrium. E would be increased and would be greater than the standard E. Now, what if the concentrations of copper-2 or cerium-3 were increased instead? Does the cell potential increase or decrease compared to the standard cell potential of positive 1.36 volts? If the concentration of either or both of these products were higher than 1 molar, then this product-favored spontaneous cell would be closer to equilibrium. E would be decreased and would be less than the standard E of positive 1.36 volts. That was primarily a qualitative treatment of non-standard cell potentials, but we can also get quantitative. The Nernst equation governs the relationship between cell potential, E, and the standard cell potential, E naught, in terms of the concentration of the cell's components. The derivation, and for the most part the use, of this equation is beyond our current needs, but here it is. If we have to use it, we'll need to use the 8.314 joules per mole Kelvin for R, Kelvin temperature for T, and the number of moles of electrons from balancing the two half reactions for N, and Faraday's constant for F. Q is the reaction quotient, that is, the law of mass action applied to a system that isn't necessarily at equilibrium. Let's see if we can use the Nernst equation to determine the cell potential for this non-standard cell with the concentration shown. We are given the balanced redox reaction and the standard cell potential as well. Before we do, let's make a qualitative prediction for this galvanic cell reaction. Do you think the non-standard cell potential E will be increased or decreased compared to the standard cell potential E naught? I'm thinking that by having a lower concentration of a reactant and a higher concentration of a product, that will put this product-favored reaction closer to equilibrium. In other words, since Q will be greater than 1 and K is greater than 1, Q will be closer to K. Since the reaction will be closer to equilibrium, it will have a lower magnitude, closer to 0, cell potential. E will be less than E naught. Let's plug the numbers into the Nernst equation to confirm. Pause the video so you can run the numbers yourself. If we plop them digits into the Nernst equation, we'll ultimately end up with a non-standard cell potential of positive 0.47 volts, which, as we predicted, is less than the standard cell potential of positive 0.48 volts. If you're wondering where the 6 moles of electrons came from when I substituted in for N, let's take a look at the balanced equation. In the equation, I see that 2 aluminum atoms are losing 3 electrons each. That's a total of 6. Or, if I look at the 3 manganese 2 ions that are each gaining 2 electrons, that's a total of 6 as well. So 6 moles of electrons are transferred per mole of reaction. Neat! Thanks for watching this video on predicting and calculating cell potentials for non-standard electrochemical cells. See you next time.